All right, everyone, we may as well get started. Welcome to your mammoth 2-hour lecture on Monday, which is going to be fun. Today, we're going to work again through the discrete event simulator, just briefly, just as a recap. I know you're all working hard on project 2. And of course, now you're seeing it a second time. If anyone wants to interrupt me and ask a question, yes, Yoni, that's correct. It's fine. Then please do that. Please interrupt me. Please ask questions. As we go through the rest of the lecture, we're going to probably go a little bit more in depth into some of the programming behind the scenes. So we'll move on to looking at what is this heap data structure? How does it work? Why is it faster than a more naive method? And then what we're going to do is look again at the more programming aspects, how to make your code more modular, more reusable. And we'll look at modules and packages and type parameters and things like that. And we'll have a little bit of time at the end to go deeper again and look how Julia actually works, think about a little bit about how it compiles the code, what makes your code fast and what might make it slow. And debugging and these kind of things. So we'll use some time at the end for that. And I believe next Monday we'll talk a little bit more about statistics and Monte Carlo before moving on to Unit 7. Okay. Just a reminder that tomorrow we have a guest lecture. Is it Anna tomorrow? I think. Again here, in the other room. I think Yoni will come and introduce Anna. So that'll be great to see her. So yeah, I hope you guys are getting something out of the guest lecturers. I think it's quite interesting. So that should be good. So anyone have anything to say before I go on? No? Okay. So discrete event simulator. So if you remember the discrete event simulator, we started with a very simple example of a queuing system where we have a bunch of phone calls in a call center. We have 5 workers making phone calls and trying to solicit donations. And we wrote this code here, and it was very specific to the problem at hand. It was sort of hard-coded, the durations and all sorts of things. And this simulate function, it initialized everything to a specific thing involving 5 workers. It involved the log or like the output that you want to generate, the kind of events that you want to see after the fact. So normally when you're on a simulation like this, the simulation might be quite meaty and take a long time for the computer. And then at the end, you kind of want to analyze it. So that's the purpose of that. And everything in here is hard-coded. We look at who's going to finish the next phone call? Okay, let's schedule them with another phone call. Okay, who's finished next? Let's schedule them. And it's all there. It's all working. And we have this plotting function, and we could sort of see the different realizations or trajectories came up with different answers. Okay, so, but on average, there was you can sort of see a trend in a plot like this. There's like a mean and a variance at any point in time. Cool. So that kind of simulation can be generalized. These kind of event simulations come up all the time in logistics, but also sometimes in physics or other aspects. Obviously, things like COVID modeling is also these kind of events, people getting infected or not. What we did is we continued on talking about a sort of class of queuing problems with the MM1 queues and the MD1 queues and the M1K queues and things. And we had a look at how we might write that simulation. This time we started passing in some of the functions like arrival function and service function here and capacity and stuff, so that you could use the one queue simulator function multiple times to run more than just one simulation. You could do a whole different class of simulations. You can do the M1 queue and the MD1 queue, depending on what you put in all these different things. So it's becoming a little bit more generic. And what you can see just as a pattern, you're passing functions into QSimulator, and QSimulator is starting to call these functions at certain points in time. Okay, but it still has to have these concepts of what the events are. The events are arrival events in a queue and service events in a queue. Okay, so people can join or leave the queue, and the state is really just the number of people in the queue. So the only thing you know about the system at any point in time is, you know, how many people in the queue, you know, what was the last time someone joined, when will the next service event occur, kind of thing. And it just progresses through time, and so on. But it did allow you to put in, no, it did not. And what it returned, it was hard-coded what it returned. It returned some function of the queue, which is just the mean queue size, okay? But you could change the code to find the variance or something else, autocorrelation, you know, how quickly does the queue size change in time, various things. So then we started to think about, how do we go and take a simulation like that and make it more generic so that it can run more different types of, you know, handle different types of states and events, and handle different kinds of outputs or logging or result collection kind of functions. So here we have taking a more structured approach, okay? So this is getting into the structure that we've given you, and you're free to use the structure for project 2 and to build upon it, okay? So here we're getting something a bit more generic, where we're starting with event and state here, okay? So these are abstract types, okay? You can't yet create an event or state. You have to define your own particular state struct, or type at least. Struct. So generally you would have, you know, for project 2, you would have to create state which is applicable to the problem at hand, okay? So you're going to create your own subtype of state, and you're going to create your own events as well to deal with that. So we have, in project 2, we have mini queues in an amusement park or something, and people hopping around from one ride to the next, okay? So, and entering and leaving the amusement park as well. So we have to think about all the different events that might occur in all the different states, okay? All the different parts of the state. So there's only, just a reminder, this is a global state. So your entire system should be described by a single state object. Now that state object, it's a compound object. It can contain lots of different things inside of it. Some of the things are constant things, like things to parameterize your system. So if we're thinking in project 2, you have matrices and vectors describing probability rates of transitions and things. And also the current state of the system, you know, so how many people are in which queue, that kind of thing. And you have to think about what subtype of state are you going to build and put into this simulator, okay? We do have a few more structure to this. So events are things which happen at time. So there's this thing called timed event, which wraps an event and has a time. You could have structured it differently. You could have said the event must carry the time, and you must, you know, we could define a function or an interface which extracts a time from an event. So when you design a generic system, like there's actually often more than one way to build it. And you have to sort of think about your users and what's going on to figure out what's going to be the most convenient. Hang on. So our project, okay, we have a question from Rachel Peach. So our project needs to include the abstract type or just a struct, okay. So if you're going to build your simulator based on the sample code, the sample code already has the abstract type for you, you would just create your struct, okay? And when you do that struct definition, you would just define it, you would declare it as a subtype of state or as event, depending on which one you're creating, okay? Yeah. So yeah, we're not really expecting you to go in and creating your own abstract type hierarchy and interfaces, but that's certainly something, it's a bit of an art to be able to create a generic API for people to use and interact with, for other programmers to use and potentially end users to use. So that's sort of an interesting field. So as I said, the timed event, it has a little bit of interface defined with it. You can compare two timed events. There's this is-less function in Julia. Now, the is-less function is very much like the little less than operator. Now, the less than operator gets a bit confused with things like nan and missing. We haven't spoken much about missing, but nan you've heard about with floating points, where you don't know whether one nan's bigger or smaller than the other nan. So it always just returns false. Is-less is a function where I think it always puts it at the beginning or something. So all the nans are less than everything, including minus infinity, okay? So is-less is sort of always returns a Boolean. It's always reflexive and transitive. It's meant to be a total ordering. All right, so we've defined a generic function process event. We haven't really attached any methods to it here, but this is something you also do when you're creating an API. You're going to want to define functions for other people to overload. So when you think about your code, you've got two things that are happening. You've got your data and you've got your functions, your procedures and that kind of thing. So Julia is a language where it's very easy to both like extend a data type, like take a subtype of some other data type or implement an interface for a data type. But it also allows you to extend or implement other people's functions, add methods to other people's functions, or create new functions for other people's data types, okay? So there's this problem in programming languages called the expression problem, where we kind of notice that, object-oriented languages tend to be really great at doing one of these, but not the other, and functional languages seem to be great at dealing with one, but not the other. But, in modern languages, they've all sort of worked around this and converged to a certain set of ideas around interfaces and traits and this kind of thing. But that's the thing. When you create an API, especially in a language like Julia, which is designed to be generic, other people can go away and take your base thing and extend it, build upon it, and it will still work. And this is what makes code truly composable and reusable. Okay. So here we're getting into the meat of it, where we actually have some concrete types. End sim event. It has no data associated with it. There's no fields. It's just struct named end. So there's nothing inside of it. And we've defined a method for process end, which just prints out a statement, says, I'm ending the simulation. It's a special event, and it actually gets dealt with in a simulator. We've created this log state event. This one just logs the state to the terminal, stand it out. It's not particularly exciting. You could, for example, create an IO buffer or something, so you're printing it to a special file or whatever you want, rather than just the terminal. There's interesting things you can do here. Okay, and here's the generic simulate function. I'll just run through it quickly. Okay, so we start with an initial state. So it says state here, but state's an abstract type. When you run an actual simulation, you're going to get a concrete state, okay, something you've defined, okay? Julia will then specialize this function, especially for that concrete state. Okay, you're going to come up, it's going to have some kind of event, initial event. For some simulations, it's going to be more suitable to have an array of events, like an unknown number of timed events. We're going to have a bunch of, at the time when it ends, a bunch of times we want to do the logging and a callback. Okay, so the callback is a generic function which defaults to not doing anything, but it lets you make recordings about the system at a given time and a state so that you can extract your results after the fact. Okay. We're defining a priority queue. So once I go through all this, we're going to go deep dive into this binary heap structure. We're going to create our own. We're going to look at we're going to put the simulation starts by putting in the end event and the log state events in. So yeah, so the advantage of these log state events here is that it's actually creating this nice vector of them in log times for you. But you could easily have put them in sort of here in an array of things if you preferred. Might be a little bit more pure. Okay, we take a deep copy of the initial state because generally you want to run the simulation multiple times. And the quickest way to run the simulation is to mutate the state as you go rather than making copies of the state, because you're going to have thousands of events. You don't want to create a whole copy of all your state every time, but it is okay to make a whole copy, a deep copy. So that means if you have vector of vectors of vectors, it's copying all the nested layers down until it gets to bytes on the computer. So you have a whole new fresh set of bytes on the computer in memory. If you edit one set of bytes, it doesn't modify the other set of bytes. And we start at time equals 0, and we do the callback sample. And we just have this very simple loop, which pops things off the priority queue, processes events. If it's an NSIM event, we break. The process event has returned a vector of events, so we put them back on the priority queue. And then we do the sampling, the callback sampling that you want to do. Okay, so again, here's an example of a specific one, which was the MD1 queue and the MK1, MM1 K queue, and so on. So we have a single queue. The state now is the number of items in the system in the queue. It's just a single number of states. So if you have a more complicated system, you're going to have, you know, for example, a collection of integers for the number of things waiting in different queues. We got all the we got definitions of what happens when an arrival occurs or when an end of service occurs. So when people arrive, we have to create the next. Not only do we modify the state here, so this is in some sense, that's the meat of it, right? The event is someone arrives, so we add a person to the queue. But the rest of the complexity here is the fact that the simulation must go on. So we have to figure out what next. So we can use our knowledge of Poisson processes to create the next event for us. Okay, so this is an event that builds other events, right? It's kind of meta. It's kind of cool. And exactly the same thing with the end of service events. The meat of it is just taking someone out of the queue, but then you've got to deal with, you know, what about the next person to get served? All right, we can run the simulation. We can look at it over time, how the queue size randomly goes higher and lower. We can modify it a bit with a callback function here, add to integral, which will let us not just plot like every single event, but just take the mean, okay? So if you have a system with thousands of different queues and millions of different events, and you want to plot that, you know, you're going to need gigabytes of memory just to hold all that state at all those different points in time. So it's much better to take your summary statistics during the simulation so you can clear that memory out and keep going forward. Okay, depending on your system, right? Like you might have a small system, you want to study it deeply, so you want to keep all the data. Okay, let's have a look. Does anyone have any questions about how this kind of generic event simulator works, or like how to use it that you want me to get through now before continuing with the content? All right. Well, if someone at home wants to write a message, just write one. I'll notice it eventually. Cool. So we're going to move on to this heap data structure. So we've talked about the heap in Unit 2. Yoni has shared this really cool video. I'll just control. All right. So this has some really cool animations that's going over the stuff I'm going to talk about today. Okay. So I do recommend it. It's just sort of like, it's good to see things a second time. I think I'm going to have to press back. Okay, cool. All right. You know, it's good to see things twice sometimes, especially if it has a little bit of complication to it. So a priority queue is something we use to quickly get the next event, okay? So we're writing a computer simulation. The computer can do, you know, a billion things, a trillion things a second. Like it's quite powerful. But it's still not powerful enough that we can be wasteful. We can't just, you know, write our computer programs however we want and expect them not to be slow, too slow, okay? So we tend to use special algorithms and data structures to make sure things go smoothly. And the heap is one that comes up in a lot of different scenarios, okay? So we could talk about lots of different data structures in this course. You know, it's actually interesting mathematics, and if you ever have a chance, I recommend it. But we're just going to talk about this one because we actually want to focus on some of the more data sciencey fun stuff as well. Cool. So what we really want this to be able to do is we want to be able to push things onto the heap, whatever we want, you know, simulation events at a time. And we want to pop off the best, the biggest or the smallest thing off the heap, you know, the soonest event or the, you know, the biggest item or whatever it is. So you can design it as a min heap or a max heap, sort of two flavors. Yeah, and we want to be able to do that quickly. Okay, so you could do this with an array. I don't think we have a nice picture of the array. So if we use an array and we kept the array sorted at all times, or if we kept the array unsorted, every time we wanted to pop off, we'd have to search every element for the smallest one at a time. So if there's n things in there, it's order n search time. But you can put one thing on the end really fast, okay, of a vector. On the other hand, if you kept the vector sorted at all times, and it was a dense vector sorted, you can always find the first element of the vector or the last really quickly in order one, constant time. But when you wanted to insert something, you might insert it to the middle and you might have to shift half the elements to the right one. So on average, the average cost of that, depending where it lands, on average, it lands in the middle. So average, you have to move n on 2 elements. So again, the cost is order n to put something into a sorted vector, okay? So we're going to be doing these millions of times and the queue length might be thousands of millions long. So it's going to be too expensive to pay this order n cost every time we do something in the simulation. We want to be able to simulate larger and larger systems. And yes, the simulation will slow down. You know, we have to do some processing for every single event. So we want the simulation to be order number of events, not like order number of events squared or something like that, right? So yeah, it's really important that we can get something faster than this order of n. And so the heap is a relatively simple data structure, and you can do both the pushing and the popping in order log n, okay? So just to give you an idea, if, you know, the queue has 1,000 things in it, and we're looking at log base 2 or something, you know, so log 2 of 1,000 is around 10, you know, log 2 of a million is around 20, log 2 of a billion, a billion is about 30, okay? So the log function grows much slower, right? You can, for most practical purposes, most programmers, when they see order log n, they just assume it's a constant small amount of time, okay? To them, it's basically, yeah, it doesn't scale with n anymore because there's already a log in there. It can be important. You can see differences between order 1 and order log n algorithms in practice sometimes, but generally it's not the biggest problem compared to this kind of speed up. It's essentially an exponential speed up we're looking at here. Okay, so the heap is related to something called a binary tree or a tree. So a tree, you can imagine having different bits of data, and you can have data is stored at a node, and a node could have children, okay? And so long as there's no cycles in this thing, you're going to get a tree. So a binary tree is one where a node can have at most 2 children, okay? So 0, 1, or 2 children. So in this picture, a node could have a child to the left or a child to the right. Okay. Cool. So, and a balanced binary tree is one where, so for example, a linked list where you go, A, B, C, D, E, that's a binary tree, but it's not a balanced binary tree. A balanced binary tree is one where the lowest or the deepest nodes are sort of minimal. Okay, so if you had n nodes, you'd expect to have around, the depth should be roughly log 2 of n. Okay, so because, on the first layer we can fit 1, on the second layer we can fit 2, on the third layer we can fit 4, on the fourth layer we can fit 8, then 16, 32, 64. So eventually you can make a tree with billions of elements, and it's still only a little bit deep. It's only like 20, 30 deep, okay? So, and then this is why it's going to be fast, because when you search or traverse through this tree structure, you might have a billion things, but the tree depth is only 30. So 30 is a lot smaller than a billion, right? So let's have a look at this tree. So if you look at a node which we call a leaf, so this node at the top we call the root. Imagine it's a tree and it's sort of upside down. This is called the root node. And then any node without children is called a leaf node. Okay, so if I just turn the laptop upside down, the people won't know, joking. The leaf nodes, the lowest leaf node is at most one level below the highest leaf node. That's the technical definition of balanced. Okay. In this case, yeah. All right, so one way of creating a balanced tree is to just start filling them in. You fill up the top, then you go left, and then you go right, and then you go boom, 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 and then you go 1,000, 1,001, 1,010, 1,011. These are binary, so they're not really 1,011. Yeah. So yeah, so that's an important point, is that it's pretty easy to attach a binary label to each of these positions based on how you traverse the tree to get to a node. So to get to this node, you start at 1, and then you go left, and then right, and then right. Okay. So the root node we always just call 1, just out of practice or whatever, convention. And then if it's a 0, you're going left. If it's a 1, you're going right. And then that way you can come up with a label. And the labeling scheme is the same as binary, starting at 1, going up to n. Okay. So in fact, because it is just binary starting at 1, going up to n, you could use like a vector in Julia to represent it. So vectors in 1, the index starts at 1. So it's kind of convenient for this particular case. And you can kind of see that if you laid it out flat in memory, in a flat array in memory, you could kind of see what the pattern of bits are. So you would basically, to get down a layer, you'd take all your bits and you'd shift them left 1. And then you would add a 0 or 1, depending on whether you went left or right at the end. Okay. And if you follow that pattern, this is the same tree structure. It has the same topology with these curved lines here. Okay. So yeah, that when we deal with computers and memory, one thing that's kind of expensive for a computer to do, a modern computer, not the first computers, they were fine. A modern computer finds it much slower to pull something from memory than it is to multiply and add it and things like that. Okay, so operations on data is really fast. It's getting the data, which is always the limitation. So if you ever look at the specs of a CPU, they talk about level 1 cache, level 2 cache, level 3 cache. You got to have RAM, you got to have a fast disk and slow disks and then network disks. If you're doing big data, you have to deal with everything from registers to, distributed file systems. So the reason for all this caching is just to get that data in as quickly as possible to the computer. So when a computer has cache, it stores like a cache line. So I can't remember what that is, 64 bytes or 64 words or something, in memory at once. Okay, so the smallest chunk of RAM that can fit in like level 1 cache is so big. So if you fit everything in next to each other, your computer might actually, your program might be like 10 times better than this kind of data structure, 10 times faster than chasing these pointers around different parts of your RAM here, there, and everywhere, okay? So a real industrial strength algorithm for a heap will use this dense thing. We're going to skip it for this expose. If you're using data structures.jl, the package, it'll use a dense structure like this underneath. And you can look at the code, it's online. We'll look at packages later on, maybe we can find it. Okay, so we're going to look at this exploded out pointer chasing version. So we have a node. A node has a value. So for this expose, this node always contains strings, and we're going to want to sort the strings by alphabetical order and figure out which is the first or last one in the dictionary kind of thing. And just here's some record keeping. A node, if it's the root node, it might not have a parent, but most nodes in the tree will have a parent. Okay, so this union thing, I don't know if you've been shown union yet. Okay, so union, so this is an abstract type again, and it just says that the parent field, it's allowed to be a nothing or it's allowed to be a node. Okay, nothing is something just built into Julia. Okay, so if we just go to the REPL and I just press enter, nothing happened, right? And oh, it's not defined. That's disappointing. If I type nothing, it will also show me nothing, and now answer will be defined. So the type of nothing is nothing, and when I print it to the REPL, it doesn't show anything. When does it come up? It comes up like this. So if false, 1. Okay, so this is an if statement without an else statement. And in this case, you're taking the else branch because false is not true. And by default, I could call that a variable, right? And I can dump or tell it's a nothing of type nothing, So it's a data type like some of those events that we saw where it doesn't contain any data. And it's built into Julia. It comes with Julia by default. It's not really built into Julia. It's just a data type defined in base or core or something. Okay. So, and then not only can a node have a parent, it can have a left child and a right child. Okay. And that's the data that it contains. Now, because we want to create a tree, you could do all sorts of awful things here. You could have a node which is itself as a parent, or has a child which points to itself or something. And then some of the algorithms that I'm going to show you, what they would do is they would recursively loop forever, and they would never terminate until you press Control-C or turn your computer off or something horrible. So what we do is we generally don't let the user construct it the way they want. We generally provide this constructor, which contains a value, and it doesn't have any kind of references. All right. And then what we're going to do is we're going to use this tree structure itself is going to be responsible for keeping track of the structure of the tree and updating those references, so that an end user doesn't kind of screw it up. Okay. So yeah. So one thing to notice here is if you haven't done some in-depth programming before, if you have a data structure like that, these nodes here, they have to actually be pointers to, or references somehow to another node. That can't be stored inline, because then you wouldn't actually know how large this struct is, because you don't know how big the tree is until runtime. Okay, so all structs, like a C program or a C++ program or whatever, the structs themselves, you know how many bytes they take in memory during compilation time. So Yeah, so there's kind of this implicit idea that these nodes, these mutable nodes, are represented by pointers to some data. And then using the pointer, you could write to that data and read from that data. That's why it's a mutable structure. You're allowed to write to it because you can point to it there, someone else can point to it, and you can write to it, and they can read from it. Whereas if you had pure data, immutable data, you couldn't sort of write and transmit a message that way. Okay, so the tree structure, the thing that we have this binary balanced binary tree struct, data type, to maintain this tree structure. It contains the number of nodes. This is just some bookkeeping, so you don't have to like count all the children to get to the last node. It contains a root node. Now, if the tree is empty, the root node might not exist, so that could be a nothing as well. So it's another union type. And again, so just so the user doesn't really get the opportunity to make a tree by hand and get the number of nodes wrong or something, we've defined this constructor here. So generally, you just call this function and it we can't give you an empty tree. Okay. Now, let's say you had a tree and you wanted to compute the depth, because that's going to be a useful function for us. Well, one thing you can do here is you can look at the log2 of the number of nodes and then floor that and round it to the nearest integer during that flooring, and then add one. And that will give you the answer. Now, there's a lot of stuff going on here. This is a integer, then we'll get cast to a floating point number. The log function's a complicated floating point thing. It's going to take nanoseconds. I mean, that doesn't sound terrible, but it's horrific for this kind of operation. And so on. So here's another way of doing it, just using the bits. So this will probably be happening in, I don't know, 1 or 2 CPU instructions or something. You look at this, you know, your 32 or 64-bit integer, and you count the number of zeros in front of it in binary form, and subtract that from the size of the integer. So I've written it this way because Julia supports 32-bit and 64-bit systems, but generally it's 64 bits. So the size of returns the number of bytes of a struct. Yeah, cool. So, or a primitive type, sorry, struct or a primitive type. Brilliant. So that's just a trick to make it faster. Again, it's taking the logarithm implicitly using that form, that binary form I showed you earlier. These kind of digits. Okay, what I've got here is, once we have a tree, we're just going to want to be able to experiment with it and play with it. So here I've created for you a very, very fancy printing function. You don't have to be quite this fancy, but generally when you have a tree, it's kind of nice to be able to see which node's connected to what node. So this thing is using these box drawing characters. So, you know, Unicode has many, many different things like emojis. And some of the Unicode things are these box drawing characters, which, you know, date way, way back to Unix and DOS and things. And you can use them to build, you know, nice looking graphics at the terminal. So what this is kind of doing is, when you have a node, it prints, you know, when you have a tree, how many things are in the tree. And then it's like, you know, constructing a graph of lines that are connecting to each other to show which parent is connected to which child. And it's passing this through these prefixes so that, you know, I'll show you what it looks like in a second. Okay, so now we want to implement sort of the important parts of this tree. So we want to, this is currently just a tree. It doesn't do anything special like ordering things like a heap will, okay? So what it's going to do is just keep it balanced. So it's a binary tree, but it's also a balanced binary tree. So when you push and pop, it's going to keep it balanced for you automatically. So when you push, what you're going to do, I mean, if the tree's empty, you just create a root node and stick it in. If the tree's not empty, you want to find the very last leaf that you should sort of fill up. You're gonna have to find a place. So to do that, we look at the binary representation of the number of nodes. Okay, so you're gonna pushing onto it. So you're gonna add one more thing. So number of nodes gets incremented by 1. Okay. And we're going to start with the most significant bit. So the bit position here. So that's the depth of the tree. This is the most significant bit. We had this earlier. And we're going to create something called a mask. So this is a number. It's just an integer, but in binary, it's an integer. It's all zeros with 1, 1 in it. And it's 1, 1 in it at exactly that most significant bit, which is the first choice. Do we go left or do we go right? Okay. But we're going to initialize it to 1 because it's the root node. Well, it's always, just going to be 1 by default. Because we know there's not 0 things. So it has to be a binary number starting with 1. All right. So we create this mask, and then we're going to use this AND operator. So AND isn't like true and false is false. AND is like take every bit and go do the AND operation on each bit one at a time, and then return a new integer. Okay. So if the position, the num, and the mask is 0, then we're going left. And if it's 1, we're going right. Okay. So this is written such that it's not equal to 0. So why is that? So let's think about this. If you're going right, you might not necessarily have 1. You might have some other larger number because the mask might not be the least significant bit. It might be somewhere in the middle. So you might end up with some power of 2. So it's easier just to check. If it's 0, we're definitely going left. If it's not 0, we're definitely going right. Okay. And then here we got this check. Are we at the end, which means are we at the least significant bit, which is the number 1. And if we've reached the end, then it's time to insert the new node. If we're not at the end, what we want to do is we just want to descend the tree. So we go current node equals the right child of the current node, and then we go back to this loop. Okay, remember we started at the root. All right. Great. And then it's the same logic going left, except the only difference here, it says L child, not R child. Okay, so it's the left one. Pop. Oh, any questions? No. Pop is going to be ever so slightly different. Okay. So for pop, what we're going to do, and this is partly because we're going to do a heap soon, is we're actually going to extract the root node and replace it. So, and then return that value. But we're going to replace the last leaf and bring it right up to the root. Okay. And this will be very, very useful operation for the heap in a few minutes. Cool. So what we do, if there's only one thing in there, then we remove it. And we just get we set the root to nothing. And that's all. Okay. Oh, and at the beginning, we've set the return value to be the root value. Okay. So we set the return value, the root value, and then delete the root. That's if it has one thing in it. Okay. We probably should put an assert that the number of nodes is not 0, right? We should throw an error probably in that case. It'll crash down here anyway, but sure. Okay. Then once we've cleared out, once we've extracted this, what we want to do is replace that value with the other value and delete the last leaf node. Okay. So this is exactly the same walking pattern as before for finding the depth, for inserting the last node. It's exactly the same thing with the mask. Okay. And every time we ascend, we move the mask a bit to the right. Again, we're checking whether we're going right or left and whether we're the last one or not the last one. Okay, so if we're not the last one, we just keep descending. If we are the last one, then we do this manipulation, and literally it's just getting the value out of the right child, putting it in the parent, all right? And then it's deleting that. Well, it's constructing a new root node essentially here and then deleting the one at the bottom. And the same here, except for the case we went left. Okay, so you can have a look at the code again in your own time if it's a little bit confusing. But let's see this thing in action. So basically, we're going to push things onto this tree. 1, 2, 3, 4, 5, 6, 7, 8, 9. And we're going to see how it lays it out. Okay, so earlier I showed you those fancy Unicode box drawing symbols. And with them, we can actually visualize the tree structure, which nodes connect to which nodes here. So the root node is 1. And that makes sense because we inserted it first, right? And then the first child of 1 is 2. That's what this one. And if we follow this line down, 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 we get to the second child of 1, which is 3. And then we start filling in. So that's the first layer. 2 and 3 are in the second layer. The next layer will contain 4, 5, 6, and 7. And then the final layer, which is half, which is only quarter full, has 8 and 9 in it attached to 4. Okay. So, you know, it's not quite like that hand-drawn diagram, but you can still see from the lines what's going on. Okay. That's pretty cool. And then we can test the pop operation. So when we pop off it, we get 1, which is the thing at the root node. And what has it done here? It's replaced the root node with 9, okay? So remember 9 was the last thing we put in. It was the last child node. And we've grabbed it and put it on top. Now it's kind of weird that we moved it, but that's extremely useful for what we're about to do with the heap. Okay, so we're going to add a little bit more structure to this thing and make it sort the elements partially as it goes. And we're going to see that order log n push and pop time. And the thing you pop off is always going to be it's a max heap. It'll be the largest element in alphabetical order, the last thing in the dictionary. Okay, so I'll just maybe talk about that for a couple minutes. And then in a few minutes, we'll take our mid-lecture break, okay? So bear with me a few more moments, and if anyone has questions, please don't be shy. So the max heap, again, it's another structure. It just, like before, we saw the tree sort of just wrapped a root node. The max heap's just going to wrap a tree. This is something you'll often see when dealing with data structures. I see it all the time. You'll have, like, you know, underneath everything at the bottom, it's always just bits and bytes on a computer, right? So everything's going to be integers and vectors and things at the bottom. And eventually more complex data structures wrap simpler data structures and give them more functionality, behavior. Okay, so here we have a constructor which creates a new max heap with an M3 balanced binary tree inside of it. When you're doing in your project and things, most of the time you're not going to need to write these constructors. You can just use the default one that it creates. Whereas in this case, we wanted to provide safe defaults, so you can't sort of accidentally screw up your data structure and make it a corrupt one by accident. Okay. All right. So what we've done here is we're overriding a method in base. So there's show method, which is what happens when you go to the thing, and yeah, we saw the show methods earlier. So it's very similar. It's just showing the nodes after telling you how many things are in it. And I will continue with this one because it's just, and then we'll have a break after this one. So sift up is this function which sort of says, if we push something to the bottom, what we want to do is we want to if it is larger, So it's a heap. So the largest thing ends up on top of the heap at the root node. So we push something on and it's larger than its parent. What we're going to do is we're going to swap it with its parent. So it goes up. And then we're going to check again. Am I larger than my next parent? And if so, I swap it. Am I larger than the next parent again? I swap and swap and swap until finally I'm smaller than one or I've reached the root node. So what sift up does is it takes a node. Okay, so if you're the root node, your parent is nothing. Okay, so if you're not the root node and you're smaller than, or your parent's value is smaller than you, then swap them. So that's what this temp thing is. So those three things just swap the values. And then you might need to percolate all the way up to the top sometimes. So sift up, we'll do that. So what we're going to do with this is every time we push something onto this heap, it's going to sift up to the top. Okay, so we push it on. Remember, it was a log n traversal to find our way down to the last layer, all right? And then we're going to sift up, which is at most log n all the way back up to the root again, okay? So, and what we're going to do, every time we push, we ensure the nodes above are always bigger than its children, okay? Now, if you think about it, that means the root node, it has to be bigger than its children, which are bigger than their children, which is bigger than all their children. So by definition, the root node is the biggest. It is the maximum value. So every time you push, you do this sift up operation, you always end up with this structure, has this invariant. The invariant is parents are larger than their children, according to the ordering. And the root node is always the largest. And you can always find the root node really fast because you know where the root node is, okay? So that's what this push thing does. It puts the value there and then sifts it up to where it needs to go to. It might stay at the bottom. It might be the right place, or it might need to go up. It really depends on this if statement there. Now, I will power through for a few minutes and then give you your break just so that this is done. When you pop off, you're going to do the reverse kind of thing. This is a helper function called last node. It just lets you descend the tree and get the final node, okay? It's the same structure with this mask. We start with the mask at the most significant bit. You know, we look whether we need to go left or right, and we keep descending. And when we're at the root, the leaf thing, when mask is 1, it means where the mask is, you know, the last bit, so it has to be a leaf. Yeah. So the shift down function, what it's going to do is, what we're going to do here is the opposite thing. We're going to put some element, after popping, you know, when we pop, we put some element in the root, and then it's going to shift down to where it needs to go. So before things were shifting up, we put something at the bottom and it shifts up. Now we're deleting the root, putting some other element there, and then we're going to shift down. So it's the mirror operation. Pop is the mirror operation of push, okay? So if there's only a left child, so the right child's nothing, but the left one isn't. So first off, in our structure with the invariants, things can have no children, a left child, or both children. It can never have only a right child. We don't have to consider that case. Okay, so if there's only a left child, we just need to compare the value of the upper of the parent with the child, and if they're the wrong way around, we swap them. Okay, and then if we've had to do that, we might need to shift it down again. So we recursively call shift down. Finally, if we're larger than both children, if there are 2 children, sorry, and we're larger than both, we don't do anything. It means it's already in the right structure where the thing at the top is bigger than things below. Now, if that's not true, we have to check something else. We don't want to just swap it with, if both children are bigger, we don't want to just swap it with either. We have to swap it with the one which is the largest. Okay, so first we compare whether the left one or the right one's bigger, and then we swap with the bigger one. Okay, and this way, again, when we pop from the tree, which puts the last leaf in the root node and returns the root value. And then we shift it down, okay, so assuming it's not empty. Then we shift that down, and then we're back in a nice state where, by definition, the thing at the top is the biggest element, okay? So we can push and pop as many times as we want, and it always takes order log n time. And when we pop, we always get the biggest thing, okay? So for example, here I've taken a heap and I've kind of pushed and popped all the prime ministers of Australia onto it. It's kind of like Australian Parliament these days. And we can kind of see what happened. So this is a max thing. So in alphabetical order, we're talking about the end of the dictionary. So Whitlam is, once we've constructed it, W for Whitlam is the last thing in this ordering. And that's fine. But if you look at the rest, it's a bit hard to see. They're not really in alphabetical order per se in any way, forward or backwards, but they are a little bit in that, you know, everything comes after its child. Okay. But, you know, here, Abbott is coming sort of in this printing before Holt. So it's not in a completely sorted order. It's not a complete tree sorted thing, but it will maintain this invariant that W's at the top. And then if we pop them off, once we put them on and then pop them off again, we actually do get them in sorted order. So we put n things on the queue, on the heap, each takes log n, and then we pop them all off, and we get them out in that sorted order. If it was a min heap, not a max heap, it would have started with Tony Abbott and ended with Gottfried Whitlam. Would have gone the other order. So this is a sorting algorithm that costs n log n. You're doing it n times. Each time it costs log n. You're doing that to put it on. You're doing that to put it off. So that's just a constant factor. So it's a sorting algorithm called the heap sort that costs n log n time and n space or something. Yeah. So obviously in the context of a discrete event simulator, we're not ordering things by string, by alphabetical order, lexical order. But, you know, we have date times or numbers that represent time, and we're sorting by that, okay? If you use datastructures.jl, you can sort of look at it here, and we'll go into that just after this. I'd like to take a 10-minute break. We'll come back at 6:08, and then we'll continue on, and we'll talk about modular software design. So how do we do things in reusable ways in software and in Julia? Okay, thanks. If anyone has any questions in the break, just type them in or come up to me. It's fine. Otherwise, yeah, chill. Yeah. Okay. Welcome back, everyone. We'll resume now. So this kind of thing, like a binary heap data structure, is something good, which could be, it's a kind of software you tend to reuse in different contexts. And there are some things you might want to do to it to make it more reusable. You might want to deal with parametric types, so there might be a not necessarily a string you want to sort, but it could be any type, including types that you haven't even heard of yet. Okay. So there's a package called datastructures.jl. I believe we've used it in this course several times already. It has structures like this min, max, heap. You're going to see it looks very similar to the kind of thing we had. It's a mutable struct, contains the values as a tree. This is one of those flat trees as a vector. So this package is going to work faster, more efficiently than what I've shown you today. It's just seeing the dangling pointer representation is just a little bit more intuitive. But you can do the same thing where instead of using pointers and references, you're using those bit patterns to index into a vector. Okay. Again, they have a nice constructor to help you build an empty one. They've got another constructor to help you build it out of a vector of elements. In fact, yeah, I think that's so you can give your own kind of tree thing. Yeah. And you look through, and it's going to have, it has functions like bubble up, like we're talking about. Instead of bubble, we've said swap or something. You got, function, you got functions about children, the number of levels, that kind of thing. Right? So it's very familiar, very similar to what we had before. This is a min-max tree, so it has a slightly different mathematical structure to let you do the min and the max simultaneously, and it's still faster than a completely sorted binary tree, self-balancing binary tree. Yeah. All right. So we're going to walk through the kind of ingredients that Julia gives you for building reusable software. Okay. So sometimes, generally speaking, when we write code, we want to make it modular, because if you have a million lines of code and they're all referring to each other in random ways, it's sort of hard to keep it all in your head and to reason about it. Okay. So when you have a very large non-modular code, spaghetti code, it's hard to think about. It makes it hard to write. It means bugs creep in. It makes it hard to edit, because like whenever you have software, it's not something that sits still. The software industry, when you guys go out and get jobs, you'll be working on teams. So you're going to start in a team. Your position is probably there either because the company's growing and everything's mad, or because someone's left and you're replacing them. Okay. So what you're going to do is you're going to turn up in this place where other people have already written all this code, and you want to be able to wrap your head around it. Okay. So if it's in nice little modules and packages with nice descriptive names of what they are, you can read some function and kind of understand, it's importing this package and it's importing that package. You can kind of understand what it's doing, because you can, read the code, you can read the English words that make up the variable names and the module names and things, and actually come up with a picture in your head what it's doing. Even though it might be one small piece of like a 1,000,000-line code base, you could still look at those 1,000 lines of code and sort of understand it in a day, even though there's another 500,000 lines of code it's referring to that you don't need to know the details of. Okay, so it's just better to write code in small self-contained pieces, just because it's a better way for humans to understand it. The computer doesn't care, the compiler doesn't care. But when you're working in teams of people and the people are coming and going and the requirements are changing, you're always adding more features or making it faster or changing it in some way, fixing a bug, you always have to get into the code and try and understand what it's doing. And that's always the bottleneck, is that your brain can only contain so much, keep in your head, so much context. Okay. So, you'll see general software recommendations like write small functions and things like that. And these kind of recommendations, what they're really trying to tell you is, write modular software. So the other aspect of modular software, which really makes it kind of interesting to me in a way, is some code's written for end users. You're going to compile a program that's going to be used by people. But a lot of code is actually these packages and modules that we're using as software developers. We're going in and we're typing using data structures, right? And it's downloading data structures.jl from the internet. And, it has its own documentation. It has its own types and functions and methods and API and interfaces and traits and things like that, which as a user of that, as a software engineer using that library, you need to learn that stuff. And so basically the simpler that is, the easier you can get your head around it, the more likely you can write lots of good code using it without creating bugs. Okay. So the modules, it's not a matter of just putting everything in boxes. It's just, these have to be neat and tidy boxes where the links from the module, from inside the module to the outside of the module is kind of minimal. And all the details about what's inside the module, you want them to be sort of, you only want to understand just the sufficient amount to use it. You don't really care how it works on the inside. So like I showed you, the code for min, max, heap here. But at the end of the day, you probably only need to know like this and push and pop or something, you know. And if you can use the constructor and push things and pop things off it, you're effective user of this thing, even though this file, you know, contains a few hundred lines of code and many different functions that it's exporting. So like, well, yeah. So yeah, so you generally want to design your software to be easy to use by other programmers. And in Julia, it's kind of, there's multiple levels of ways that they've encouraged code to be shared and reused. Some of it's the community stuff, you know, just an encouragement to get academic and industry people together and to write things open source. Some of it's the fact that there's this convenient package manager, which makes it easy to take code on your computer and then put it on the internet for everyone else to use, and vice versa, for you to download the code that other people have written. And then there's the language features, the lower level language features. So some of them is just like, we're going to talk through modules and how packages work, but also some of it is the actual design of Julia. When the creators created Julia, they were thinking very hard about how to make code reusable for mathematicians, okay? Which is, you know, which really leads to why we chose this programming language for this course. Because to some extent they seem to have succeeded in this. But yeah, there's plenty of programming languages, and all of them have, all modern ones, they have great package managers, great package ecosystem things you can download, and ways to make the code easy to sort of bring in and use in your own code base and extend and so on. Okay. But yeah, I'll talk about kind of some of the features, some of the mechanistic features, and later on maybe a few of the kind of ways to design an API in Julia to be reusable and extendable. The first obvious thing to do, I mean, we've discussed a lot of things already. We've discussed functions and data types. Like you can create your own structs. Structs a way of taking lots of different bits of data and putting them in something and hiding all the details, okay? And then you use functions to manipulate the struct to get things out of it and put things in, just like we did with the heap, okay? So that makes it nice and modular. But the code itself is text. It's lines of code in a file somewhere, or multiple files, okay? So the way you can kind of organize it, apart from the files themselves, and there's an include function for reading another file and evaluating it, is modules. Okay, so we've heard about packages and we've heard about modules, and they are two different things, but the packages are strongly coupled to modules, but modules are what's sort of underneath them. So you can think of a module, it's a namespace. It's a thing which holds variables, functions, types, and stuff like that. Okay, so in a module, you know, you can create variables. The variables can be dynamically typed, flexible things that you can write over, or they can be consts and well typed. Okay, functions. We've seen generic functions. Functions are containers for methods, essentially, and then there's various types. There's primitive types, unions, structs, mutable structs, abstract types. In Julia, union all types. So these things can all live inside a module. So when you start Julia, there's already 3 modules in existence. There's one called core. So that contains everything in Julia, which is kind of intrinsic. It needs to be there in order for Julia to make sense. So much of the compiler in Julia is written in Julia. Okay, so the core module contains a submodule called compiler, which has all the type inference and optimization code. Okay, it could contain more and more of the compiler over time, essentially parsing, lowering code generation and stuff. But currently they have different systems for different parts of the compiler pipeline. But if you're going to write something like a compiler, you need certain things. You need things like numbers, strings, you know, basic built-in types to actually create a compiler, right? So like array, you can't write a compiler out of vectors and dictionaries and things. So there's a version of vector and dictionary in core with some basic functionality. There's this thing called base. This is the standard library that contains everything we use when you start the REPL. Well, not everything, but most of it. The REPL itself has been factored out into its own package or module. But yeah, when you start Julia, you have strings, characters, various types of numbers, addition, subtraction. You have all these different things. And the base library is pretty extensive in Julia, which is kind of nice. And then there's something called main. So when Julia starts up, core and base, they kind of pre-exist. They're the Julia people write that code and release it to you. So like core and base are mostly written in Julia. You could, if you want to, you can. It's an open source project. You can contribute to that on GitHub and write that code. But the code that appears on your computer when you run the REPL or when you execute a program, when Julia starts, it creates this empty module called main, and it just sticks base in it, and that's about it. Okay, so so when I start the REPL, there are these modules called core, base, and main. Yeah, and main is the module that everything in the REPL happens in. So if I go like x equals 1, that is main.x, right? It's not core.x. That won't exist. Okay, so when I type things at the REPL or I put it into a file and execute the file, which will include the file, what it's doing is it's defining variables and functions and types inside a module. And the default one is main. So you start Julia, it creates main, it puts base in it, and imports the basic, is using base essentially, and then you're away. That's it. So yeah. To create a module, there's this module keyword. It's a bit like the struct keyword. You go module thing and then end at the end, and then you stick stuff in the middle. Now, we don't normally indent this because otherwise your entire file would be indented and it's kind of looks silly. But that's just a convention. You could probably indent that out 4 spaces, but then every Julia file would have 4 spaces at the front of it. Yeah. And so I'm going to copy and paste this for you into the REPL. So we've just created this thing called my module. Right, it has stuff in it. It has a variable. It has this function, and so on. It also has base inside of it because by default, modules import base. There's this thing called bare module, which you would use if you're a compiler writer or something. It creates a module with no imports by default. Okay. Modules can be nested. So modules can contain modules, can contain modules. It's a hierarchy. And when you start using or importing modules, you're also getting a kind of a reference to the same module. So it sort of becomes a DAG eventually. But a module is always defined inside another module. So, so every module has a parent module. So it was defined in main. Okay. Now these modules that I spoke about, those 3 ones that come with, they're kind of their own parents. Like there's kind of 2 universes. There's kind of the core universe and then main universe. The core stuff you don't mess with because then Julia crashes. All right, modules. They now when you're using an import, these 2 keywords, they are commands to the package manager to go load some code for you. Okay, the special loading logic. So by default, it will look in the package manager for the package called that thing. If you want to use or import a module, you put a dot in front of it to talk about a module in your current scope. Or you could, if it's a module in your parent module, you can use like dot dot things. So it's a bit like, directory kind of things with the dot dot dots and stuff. Yeah. And just to note, when you're creating modules, it's good to give them a good name so that people kind of know what it is. So something that describes what it does. If your module creates a single, if the idea of the module is to construct like a data type, so we're going to look at a max heap module. You can't really export something with the same name as your module. It sort of otherwise becomes ambiguous which one you mean. So generally you just pluralize it. So you have the data frames package that deals with, exports a data frame and that kind of thing. So as an example, here's a max heap module. It defines a bunch of stuff in it. So there's this module, just like functions, you can put a doc string in for the module. So people can go ? Max heaps, and it will tell them an overview of what's in the module, what can you do with it, kind of thing. So you can document everything in your code. So we're going to create this max heaps thing, but we're going to do one more thing to make it more reusable, and that is to add a type parameter to node and balanced binary tree and max heap. I have a question from Emma Comino. So is using used to import an entire package, but then we use import for, yes. So when you extend or modify something from another package, you have to import it. If you type using, it will let you read it and use it, call the function, but it won't let you edit it. So you can do two things. You can specifically import, say, base.isless, or you can refer to it. You can go function base.isless thing so that it knows which isless function you mean, because there could be an isless function in your module and an isless function in base. And it has to know which one you're referring to. And so by default, it wants to create everything inside your own module. So if base exports a new function in the future, and that name clashes with some function you've already created, you don't want your code to crash. Your code is thinking about your function. So it take your local modules, methods, and functions take precedence over the base ones. So yeah, I don't know if that gets confusing for anyone. Just shoot us some questions on Piazza or something. That it is a bit of a funny one, the import versus using and when you'll add override functions and things. In here, we'll show you an approach I tend to take these days. I think I've changed my mind a few times over the years. So this is a module called max heaps. It exports a max heap. Okay, that's defined further down. Generally, you'd put the exports at the top just so that when you look at the code, you kind of know what it's about, what are the things I can use. It's more of a documentation thing for developers. Now what we've done is we've parameterized node by T, which is T is an arbitrary data type. So a node can contain a value of type T, okay? And children of type node T or nothing. And there's a little bit of syntax here around defining, these functions. If you call node T for any value of T, then call new with this. And I'll put this convert in here so that it'll convert in 32s and in 64s for you and stuff nicely. I put here next all the functions on nodes. Shift up, shift down, show node. Yeah. Then we got the balanced binary tree. Again, it's parameterized by T with a very similar pattern here for the constructor. Note here that when you define these functions, you don't have to put this T here if you don't want. Like there's no T here. So this method applies to all balanced binary trees, no matter what T is. If I wanted to specifically do it something special when T was an integer or something, then I could add more type constraints there. But by default, you don't need to put any. you can push and pop things. So I've just literally copied and pasted the code from before and added type parameters and put it all together. And then we got the max heap. What I've done here is I've attached a doc string to that so the users can have some idea of how to maybe use it. So this function returns an empty max heap that can hold elements type T. Items can be added using push and removed using pop. And the maximum item is always returned by pop. Okay, so that's basically everything a user needs to know about max heap, right? So there's this module called max heaps. It exports one thing called max heap. It has some pretty minimal documentation about how to use it. But it should be enough to get anyone started. And then here's some methods about that. So if you see here, I've got this base dot push here. So rather than importing everything Emma, what I do here is just prefix it at the method definition. So this just makes it clear to the compiler that the function that I want to apply this method to is base.push, not maxheaps.push. Okay, because there is no maxheaps.push. So, but if I didn't put base dot there, it would just assume I meant create a new function called maxheaps.push. Okay. Yeah, and so we're overriding show and pop and everything here. And that just creates a module, all right? That's fine. So I can copy and paste this into the REPL. Yeah. And it's a lot of code, but it can handle it. I can do, for example, using .maxheaps, I can construct heap. Let's make it of integers, for example. It should work. And then I should be able to like push various integers into, oh no, it's broken. I don't know why that's broken, but it's broken. That's weird. What have we got here? Nothing like some live debugging. Okay, so base.push maxi value string. Oh, okay. So that obviously that's that change with the T thing. So I can probably edit this at the REPL nice and easily. Yeah. That doesn't have to be a string. String. Probably got the same problem on the tree. Yeah. So it's interesting that the REPL can be somewhat usable. I won't import it again. I don't think it likes importing things twice. No, it's still kind of upset at me. We're going to edit this in a minute anyway in our text editor. Sorry about that. So files and modules in Julia are completely decoupled. Files can include other files arbitrarily, and modules can, you can have multiple modules in a file. The syntax in a file has to be kind of complete. So the begin module and the end module statement have to be in the same file. And you use the include function to include files, okay? And so this is just a nice piece of functionality you can use anywhere. But when you're using packages, there's some kind of direction or guidance into how your files and your modules should be for a package. Okay, so packages are designed for sharing code, so there's some conventions about them, so that the package manager can deal with it and everyone can use it. So a package called foo must contain a module called foo, and that module has to be defined in a file called source/foo.jl. Okay, so when you go using whatever, it'll find the module in the directory, the package. If you can type using foo, it will ask the package manager, where is foo? And then it will look in the source.foo.jl file, include it, and then return the module. Well, yeah. And the root directory must contain this file called package.toml, and that contains a few key pieces of information. Packages have to have a name, foo in this case, and everyone gets a unique ID. So anyone out there in the crowd might decide to also create a package called foo, and we don't want the package manager to explode just because two packages happen to be called the same thing. So they all have this UUID, which is like 128 bits of random numbers, so they don't clash. There's optionally a manifest file, which defines exactly the version of every dependency and the dependencies that your package uses. This is useful in production systems, particularly where you don't want all the code out there from the internet you downloaded to be changing every day, and your program to work some days and not work other days, or your server to crash some days, that kind of thing. So it's good practice to precisely define the software you're using all the way down to the lowest level. You can use Git repository, so the package manager registry by default uses Git for sharing code. It's sort of being evolved into a more generic mechanism, but that's historically been the case. And it handles things like unit tests for you, building dependencies if you have binary dependencies. It handles things like this as well. Okay. So that's packages. So packages are a thing, they're almost a little bit external to the Julia programming language. They're a thing that Julia has built-in functionality to deal with. It can load packages, download packages from the internet and run them for you. And it's built into Julia, but it's a part of the Julia sort of environment, but it's not really necessarily part of the Julia language per se, almost. Okay, so we have a little bit of time, and I'm going to show you how to create a package at the REPL, okay? So I am in a directory called lecture. I'll move this down so you can see me. All right. Here we go. And there's nothing in here, I don't think. Yeah, so well, I'm going to go into Julia. I'm going to press the right square bracket to go into package mode. I'm going to ask it to generate a package called max heaps. All right. It's created that package, okay? So if I have a look, it's created a directory called max heaps. It has the project toml, and it has the source file with max heaps in it. So that was the stuff I mentioned that has to be in a package, right? So we'll look at this in a minute. I'll go back into Julia briefly, and we'll go develop max heaps. Now what this does is it adds max heaps to the list of packages in my environment. So at this point, I'm allowed to type using max heaps, and that will work, okay? Great. So I'm gonna now open Visual Studio Code. Yes, I trust the author some days. And we'll see if we can make it a bit bigger. Okay, so there's this max heaps thing. And by default, the generate function gives you this hello world function for you. And there's this project toml, which has the name of it, a random UUID. The author's thing, it grabbed that from my Git config, and a version. So it's not version 1 yet, because it's still being developed. Okay. I had here some nice module code. All right. And I'm going to put it here, save it. Let me just go look for all this string stuff, and we'll delete everything with string. Screwing with this a little. And then there was a problem with the nodes, wasn't there? Oh, I didn't know how to define the node. So I'm going to go like node value equals node value. That we should probably actually fix that up though. should work. So creating new nodes. Yeah, that should be fine. Good. All right. Now I have installed on my computer a package called Revise. Why on earth is it? Okay. Oh, that's hilarious. So Revise is a package which watches the files on your computer for the packages you've already loaded, and it recompiles them for you as you edit it. So that pause I just had where I was like, what the, was it actually compiling the code that I just gave it? Okay. So it even has an export now called max heap, because I'm using max heaps, and I should be able to go heap equals, I should be able to do that. I won't need to do that anymore. Hurrah. And if I'm lucky, I can push things to it. All right. Yeah. And then I can do things like while heap.tree.node doesn't become nothing. Show pop. I don't know. We're just going to empty it now. No, it's not node. Root. Let's empty it. Here we go. So now they've come out in sorted order from highest to lowest. Okay. So in a matter of seconds, really, we've created a package. If I wanted to make it an open source package, I would turn it into a Git repository. I would push it to GitHub, and you can either use some tooling, which is now built into VS Code, to release it to the ecosystem. So like in the Julia VS Code extension, you can go Control-Shift-P and you can go, I think, I don't know. Anyway, there's a command in here for releasing your package to the package ecosystem and letting other people use your open source code. So yeah, the other thing I will just briefly show you is that if I was doing this for real, I would probably create like node.jl. Oops, what have I done? Tree.jl, heap.jl. I'll probably do it like this. So just to make it a little bit easier to navigate. And then I'd go in here and I'd take all the code relating to nodes. And I would put it in here. Then I would take all the code about the tree. I'll put it here. And then I would take all the code about the heap itself. Put it in here. And then I would go like include node.jl, include tree.jl, include heap.jl. So this is just, we're getting very close to this being a usable package. So if I put it in Git and added unit tests, it'd probably be already good enough that you could just put it out there as an open source package and people will be able to download it on their computers tomorrow. Okay, so if you know what you're doing, it's a matter of minutes. If you want to figure it out, there's a lot of documentation about it. If contributing anything open source is interest to you, but certainly creating packages is something that's not too challenging. You don't need to create a package for project 2. We are considering whether that's part of project 3 or not. Yeah, but yeah, at this stage, feel free to organize your code how you like, but modules may be a thing you find helpful or not. So that's you. All right. I thought we got a quarter of an hour. you only asked me to talk a little bit about my experience sort of developing software, open source software, closed source software, how to make packages and things. So I'll talk a little bit about that, and then we'll talk a little bit about Julia compilation as a kind of bonus subject. So over the years, both as a postdoc and working in industry, certainly used a lot of open source software and started to contribute things that I've created. When you find you're using things over and over again and the tools you currently have are kind of painful, sometimes you can kind of get motivated and spend a late night creating an abomination, which you spend the next year trying to make less bad, because people are yelling it on the internet. It's probably not quite that bad. But certainly, I do have some experience creating things which other people use. And it's kind of a really interesting experience, because at first it's sort of exciting. And then people start to use it, and it becomes like a thing of its own life. And this is the same for private software. So if you're working for a company, it's exactly the same experience. Once other people use your software, it's kind of a product, whether you're being paid for it or not. It's something people tend to expect to work without bugs. And then they ask you, why doesn't it have this feature? Why isn't it faster? And this kind of thing. So you probably spend, 10% of the effort creating it, and then like 90% of the effort sort of maintaining it over time. Interestingly, things which sort of tend to have more users, things like data frames, which is a big package in Julia. Static arrays is one I've written, which people use, they're to make working with like short vectors, like 3 vectors and things faster. They get a lot of users, and also a lot of people developing it. So in an open source project, you get collaborators that come online, and you try and help them at first, and then they eventually help you back later. When you're working on code in industry, you've probably got code you've created, and you're going to have to walk other people through it. And eventually they'll probably take it over, and you can finally work on something else, and you're no longer stuck. So it's sort of really important when you structure your code to make it clear, so that people aren't scared of it, so that they can come on board, read it, understand it. And if they have a problem, they're empowered to fix it themselves, which is great for them, but it's fantastic for you also, because you're no longer stuck being the only person in the world able to be yelled at on the internet about this one particular issue. So here are a few packages. Some of them we'll look at potentially in Unit 7. This is 6 here, Unit 7. Okay, so these are dealing with manipulating data and tables and things like that. I'm hoping we'll also spend a lot of time looking at data frames, which is another awesome package that I haven't really been involved in. Okay, so if you look at any of these packages, if I look at, say, static arrays, for example, it's sort of hard to just get rid of those. Click on it. You can sort of see this stuff. It has like a README file. It has, people are using it. 114 people forked it. These people have said they're using it. There's 119 issues or bugs, essentially. 31 pull requests, some of which will be old and stale, and some of which will be new, that people are doing. If you click on any one of these, there's probably a bit of back and forth between multiple people. And this isn't unusual. This kind of discussion is what you have internally in a company or externally on the internet for open source. It's a pull request, so what it's going to do is, in this case, it adds 2 lines of code. And then you can press a button like this to approve it. I can press a button over here to merge it, or I can close it, various things like this. Okay, so yeah. So it's kind of interesting. Cool. So maybe I'll talk a little bit about these items down here. And what we're going to do is we're going to circle back to just give a more complete overview of some Monte Carlo things next Monday. So just for the last little bit, anyone have any cool questions? Oh, here we go. So yeah, that's right. So Catriona, the way people communicate with you generally in Julia, one, if you have a package, they might create an issue on GitHub, which is like usually a bug report or a feature request, but it could be anything. But in a lot of communities, there's different chat boards and groups and things. So there's a Slack and a Discourse server for Julia. So a lot of questions end up on there. There's Stack Overflow. But yeah, generally people don't directly email each other. It usually goes through the platform of the code's hosted on, or the environment uses. Different languages will have different Slacks or Discord or something, Reddit, that kind of thing. Yeah, so Julia, all right. Julia is a programming language which has a few interesting features. One of the things you may kind of see is there's meta.parse. Okay. There is the ability to sort of compile your code in Julia. Okay, so here we have a string 1 + 1, and we can turn that into some object, which is called an expression. Okay. I'm going to run dump. So dump just recursively, puts all the things in the struct out. So I'm going to dump the expression. So an expression is something that has a head. The head basically describes, well, it's a Lisp term for the first thing in the list, but in this case, it basically describes what the expression is. So this is a call expression. It doesn't look like one, but it's actually a call expression. You're calling plus, so 1 + 1 is the same as this. Okay, so plus is a generic function with lots of methods because plus is a common operation. All right, and then I can evaluate an expression, and that will take all that code. So when you go include, it will parse, it will open a file, read it as a string, parse it into an expression, and then evaluate it. Okay, that's what include does. But there's a lot going on at evaluation time that we can look at. Generally, things that happen at top level, like if I type 1 + 1, or sorry, if I go something like this is going to call some other code. Okay, it's going to call this add int function. Okay, so there's this function in base called add int, I think. Yep. Actually, that's a function in core, is it? That's something that comes with Julia before you write any code, right? It wouldn't work without it. Cool. So, and if I want to see what's going on inside a function like this, which is a really simple function, I can see what Julia is going to compile. So I'm going to show you a bunch of macros. I don't expect you to remember them all. It's just sort of for interest's sake. So this thing is the kind of the description of what's happening inside that function. So between the expression that I showed you before, expr, right, or whatever, and actually getting an answer, there's several layers in the pipeline. First, the grammar or the syntax is transformed. Okay, so some things in the Julia language are syntax sugar. So if I go, if I say a vector is like, 10, 20, 30, right? And I go like V2, right? that's actually sugar for get index v2. Okay, so if I go meta.parse v2, sorry, it hasn't, it's still this thing called a ref. But if I lower that, is that a thing here? Maybe it has to be. Yep. Maybe it's I have to lower an expression probably. I should have prepared this at home. Well, it transforms that syntax. It gets rid of all the syntax sugar. It converts indexing into get index. It converts, setting things like plus equals. It will convert x plus equals 1 to x equals x plus 1, and things like this. Okay, so it'll do a syntax transformation called lowering. Earlier, this code lowered is sort of after that really surface level syntax has been removed. Okay, so during lowering it sort of puts it in this form. It creates kind of dummy variables like %1. %1 is add in of x and y. Okay, that's what. And then I can keep looking at this. I could look at what does the code look like after it's done some analysis on it. So it now does typing. So we know that x and y in this case are int64s, and type inference says that when you add an int64 to int64, you get an int64 back, and that's the typed code. Okay. And I can't remember if this has, no, that might be fine. Then it turns this into a type of assembly code called LLVM, which is, LLVMs are kind of a compiler thing. And then it will turn LLVM for you, will turn that into native code. So this is like Intel assembly language, because I have an Intel computer. If I had an ARM computer, it would be ARM assembly language. And that's what's running. So the computer itself, this is sort of written out in ASCII, but in reality, this is a handful of bytes. Okay, and there's a byte code associated with x86, and there's a byte code associated with ARM and RISC-V and various things. So it's like, you can imagine there's 4 stages. And what usually goes wrong with your code is the type inference. So if Julia can't figure out that the return type of a function, then it can't put aside enough bytes for whatever that data is. So it gives up. It says, oh, it's some data. I don't know how big it is. It could be 0 bytes, it could be 100 bytes. So I'm going to create a pointer to some random place in memory, and I'm going to dynamically allocate that memory. And every time I want to access it, I first have to look up the type dynamically and do some processing, and then figure out, oh, that's an integer. So that means when I want to call the plus function, I have to call this version of the plus function that's good for unsigned integers or something, yeah. So that's basically all I wanted to say there. Yeah, so of all these tools, when you have, and I will get into this hopefully before we finish this course, is that if your code's running a lot slower than you expect, it's probably because type inference has failed to figure out what you're trying to do. And do you remember when we added a type parameter to like node, for example? Yeah. A type parameter here, so value t. So one way of doing this is I could have just done that. I called it any. But this is the problem where Julia won't know the type of it at compile time, and then it will run much slower than it could. Okay. that's 7 o'clock. That's roughly where I wanted to get to today. I hope you've enjoyed the lesson. It hasn't been too tough. It's probably been a bit of a wild ride. Please let us know if there's any kind of questions or follow-ups. We'll be here, well, next door tomorrow with Anna, and after that we'll have another, I think we're going to have another consultation hour, I presume. We talk about project 2 and you've got your cheats. So thank you very much. Good.